In this video, we solve problem 14.6.022 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're asked to use a triple integral to find the volume of the solid bounded by the graphs of the equations z equals 7 minus x cubed, y equals negative x squared plus 3, y equals 0, z equals 0, and x is greater than or equal to 0. Now these first four represent surfaces. X equals 0 is a surface, and then x greater than 0 is a subset of three-dimensional space. We just want to graph those four surfaces and the boundary surface for this region and use that to infer what our solid looks like. And then once we have a picture of our solid, we can come up with the appropriate bounds for a triple integral representing its volume and then evaluate the integral to find the volume. So let's start by graphing. Okay, so we're gonna graph our surface, or our solid, excuse me, in three-dimensional space. Remember that x-axis is sort of pointing out at us. The y-axis usually goes off to the right, and the z-axis goes straight up. Now I think what I'm going to do is I'm going to graph these first, and I'll just remind you how these are related to the three coordinate planes, and then we will graph these two guys. Now, we don't actually have standard forms of equations for these two guys. They're not quadric surfaces. But since this does not involve y, this is a cylinder with rulings parallel to the y-axis. And since this equation does not involve z, this is a cylinder with rulings parallel to the z-axis. So we're going to use those pieces together, but let's graph these guys first. Now remember, in three-dimensional space, let's say we're in a classroom and I'm your teacher and I'm sort of standing at the board. Here I am. Let's make sure I've got two legs, okay? If I put my right arm straight forward, let's get rid of those arms. My right arm would point in the direction of the x-axis. If I put my left arm to the left, that's going to point in the direction of the y-axis. And then my torso is pointing in the direction of the z-axis. We call this a right-handed coordinate system because the positive x-axis is going in the direction of my right hand and the y-axis is going off to the left. So that's what makes it right-handed. Now, the YZ plane is the plane that's right behind me. So if I'm in the classroom, like that's the plane where the board is. This is the YZ plane. And in the YZ plane, x is equal to 0. Now the XY plane is where I'm standing, that's the floor. And if there's a wall to my right, this is relative to me when I'm looking out at you, that is the XZ plane. Okay, so if you're saying to yourself, what does that have to do with this? I'm getting to that. Y equals 0 corresponds to the XZ plane. So it's this plane back here. It's that right wall. And it would actually be the right wall, or the wall on that, well, it's the same wall that would be in the classroom next door to me as well. It would go beyond that z-axis where x is negative. So this is y equals 0. That's the XZ plane. Y equals 1 is parallel to that, and y equals 2 is parallel to that, and y equals 3 is parallel to that. Y gets, we end up with all of these parallel planes, y equals k, and they're all parallel to that right wall, the XY plane. You can imagine them sort of standing up like this. You've got a grid like this. There's y equals one value, and then y equals another value, and then y equals another value, and another value, and y equals another value, and another value, and so on. So y equals 0 is back here. and that's the negative x-axis. Z equals 0 is the xy plane. If z equals 1, we are on a plane that's parallel to the xy plane that's just up 1 unit. Z equals 2, that's up 1 unit again. Z equals, let's say, 10, maybe the ceilings are 10 feet high, like that's going to be where my ceiling is. But z equals 0 is the xy plane. So that's this plane down here. And then, as I said before, this is the YZ plane, that's where the board is. And the YZ plane is given by x equals 0. X equals 1 is a plane that's 1 unit closer to us. X equals 2 is a plane that's 1 unit closer to us after that. So if the x planes sort of look like this, the y planes look like this, and the z planes are like stacked like that. That's like z equals 1, and that's z equals 2, and that's z equals 3, and z equals 4, and so on. It's really hard to illustrate via Zoom, but we do the best we can. So that's x equals 0 back there where the board is. So we've got y equals 0 here. Z equals 0. That's the xy plane. Now I'm just going to draw the part of it where x is positive, because that's the part we're interested in. So it's y equals 0 and z equals 0 and x equals 0 is that plane in the board behind me. So you put these three pieces together and you get something that looks a little bit like a rectangular box. Okay. And we are interested in a surface that lives bounded by this plane and this plane, and x is greater than or equal to 0. So we're probably going to be right here in that first octant. Okay, so we've got those surfaces, and we know that x is positive. Now we want to graph these other two surfaces. Now these are a little bit harder to graph, but we can actually graph them in 2D and then extend our graphs to 3D. So let's focus on that first curve. Actually, let's do the y equals negative x squared plus 3 first, or y equals 3 minus x squared first. I think we all know what that looks like. Y equals x squared is a parabola. When you multiply that by -1, it flips that parabola upside down. If you add 3 to it, it moves the parabola up 3 units. So when x is 0, y is 3. And then when y is 0, we have 0 equals 3 minus x squared. We get x squared equals 3. So x equals plus or minus the square root of 3. And you can look that up. That's approximately 1.7. So you've got a parabola facing down, and it looks roughly like this. Now, we don't have the whole parabola. We're only interested in the part where x is greater than or equal to 0, so that's this side. And we're also bounded by y equals 0, so that's the x-axis. And x equals 0. X equals 0, it's going to lie right on top of the y-axis, like this. So putting those three pieces together, I see that my solid is going to lie above this region where x is greater than or equal to 0, and it's bounded by this line and this line and this. Now you might be saying to yourself, how is that a surface? And that's an excellent question. Right now, this is just a curve in two-dimensional space. But remember, we're not thinking of this as a curve. We're thinking of this as a surface in three-dimensional space. y is equal to this, and z is free to be anything. Z can take on any value. When z equals 0, y equals this. When z equals 1, y equals this. When z equals 3, y equals this. When z equals negative 17, y equals 3 minus x squared. Y equals 3 minus x squared all the time, and z is free to be anything. So what we end up with is a parabolic cylinder. It's sort of coming out of the page, and it looks like this. Now I'm going to share my screen with you. I'll show you how to graph this. Let's see. Screen share. Now what I'm showing you is what's called Calc 3D. If you just Google this, you'll be able to find this. It gives you options to graph surfaces in 3D. It says, okay, well, it's having a problem with graphing nothing. But what I'd like to graph is y as a function of x. So I go up here to graph and then select y as a function of x and z. And I want to graph y equals 3 minus x squared. Remember, it's a parabola in the xy plane, and z is free to be anything. You see it? So there's the x-axis. The y-axis is hidden now, and z is free to be anything. So that's what we've got here. That's what I'm imagining when I put this little index card over this parabola right here. There's my x-axis, there's my y-axis. My z-axis is going in the direction of my thumb, and then this is coming up like that. Okay, so how does that translate to this picture? Well, we're going to go 3 units in the y direction, like this. And then this surface intersects the x-axis at plus or minus square root of 3. Okay. So we have to imagine this. Now I didn't draw the whole parabola because I just wanted this part. And this region contains the origin and the parabola and the x-axis and the y-axis. That's this region right here. So our solid is going to lie above this. And actually remember that we're going to see this coming up out of the page. Now at the same time, z is equal to 7 minus x cubed. Now traditionally, if I were to graph that z equals 7 minus x cubed, I would put the z-axis here and the x-axis over on the right. But I don't want to put the x-axis on the right this time because I'm in a right-handed coordinate system, and this x-axis is sort of coming out at us like this. Because of the right-handed coordinate system, I'm going to choose to put my x-axis right there. So that way I could take this xz plane and I can turn it, and then it'll look like this picture. What I'd like to graph now is z equals 7 minus x cubed. When x equals 0, I think we can all see that z equals 7. Let's put that up there. And when z equals 0, we get x cubed equals 7. So x equals the cube root of 7, which is about 1.9. Now, since this is the positive x direction, the positive cube root of 7 is going to lie right there, and it's going to look roughly like this. Now, if you're saying to yourself, sorry, that's the work from the other function. If you're saying to yourself, that doesn't look like 7 minus x cubed, that looks like 7 plus x cubed, you're absolutely right. The reason why it looks off is because we've got this positive x-axis on the left instead of on the right. But this is correct. When z equals a positive cube root of 7, when x equals a positive cube root of 7, z equals 0. And so the graph is going to look like this. But again, we're interested in the part of the graph where x is positive. So I just want this piece. When I graph over here, I'm taking this and I'm extending it into 3D. remember we've got z is equal to 7 minus x cubed. So this is what it looks like in the xz plane when y equals 0. But y is free to be anything. So we're going to see this exact same shape. When y equals 0, we're going to see it. When y equals 1, we're going to see it. When y equals 2, we're going to see it, and so on. I'd like to show you, again, by sharing my screen. Now, I can't graph 7 minus x cubed because I have trouble changing the bounds for z here. Now, they just put in a function that they automatically start us all off with on Calc 3D. I want to use z equals, let's say, 2 minus x cubed. It's going to have the same shape. It's just going to go up 2 units rather than 7 units so that we can see it. You see it? On the xz plane, it looks like that. So there's that shape that I drew right here, but y is free to be anything. So that's what you're going to see in 3D. Having a little bit of trouble rotating this guy. Okay, so we're going to see that cubic shape, and it's true when y equals 0, and when y equals 1, and when y equals 2, and when y equals 3, and when y equals -3, and y equals -10. It doesn't matter what y is. Z is equal to 7 minus x cubed, and we get this shape. Now, it's going to be hard to imagine what happens when you intersect these two guys, and I'm going to change this value of the y-intercept to make this picture a little bit easier for us to see as well. But if you take a parabola facing down for y, and you take that cubic cylinder, z is a function of x, and it's cubic like this is what you're going to get. You're going to get a solid that has this cubic function on the top, and that parabolic function is going to intersect on a curve. It's not rendering very well, even though I love this graphing software. You should just check it out. Just Google Calc Plot 3D, and it'll help you visualize your functions. Okay, so that's the idea. We've got this intersecting over here. This is what we're going to see over here, and the cube root of 7 is about 1.9, and the square root of 3 is about 1.7. So this actually would intersect over here. It's beyond this guy right here. It's beyond that square root of 3, where the parabola is intersecting the x-axis. So this is not to scale. When z equals 7, x equals 0, and when z equals 0, x equals cube root of 7. And so we would see something that looks like this. That was actually supposed to be that curve right there, but in 3D. And then the rest of it would go beyond, it'd go behind that x equals 0, that yz plane. It'd go that way, and we just keep seeing it over and over and over again. But let's figure out where our solid is going to intersect the xz plane. When x equals the square root of 3, so that we're right here, y will equal 0, and z will equal 7 minus the square root of 3 cubed. Sorry about that reflection. And that's about 1.8. It's going to intersect up here, something like that. And when x is 0, because we're in the x or in the yz plane, z is 7 and y is 3. Which I think makes sense to all of us. When x is 0, z is going to be 7 the whole time, and y is going to be 3 the whole time. So that's the point. X equals 0, y equals 3, z equals 7. And that point lies on this graph and on this graph. So what we're going to see is something that looks like this. This is that parabolic cylinder given by y equals 3 minus x squared. And it's intersecting that cubic cylinder and they're meeting on a curve that looks something like this. Thank you so much for your patience. I know it's really hard to graph these guys, but I think that graphing helps. It helps us visualize what's going on. Okay, so we want the solid that's bounded by this, and that plane, this plane, and this plane, and we want x to be greater than or equal to 0. So we want the solid that's above that region right there. Well, in order to do that, we graph first, and we have. Good for us. It took a while, but we got it. And now we need to think about what the bounds for z would be, and what the bounds for y would be, and the bounds for x. Oops, I just started writing. We start here in the xy plane at z equals 0. So the bottom function for z is 0, and the top function is that cubic cylinder, z equals 7 minus x cubed. And to find the bounds for y and x, we just look at this region right here. And there are a couple of different ways that you can describe it. But one of them involves y going from a function to a function and x going from a constant to a constant. The constants are easy. X goes from 0 to square root of 3. And actually the y bounds are easy as well. Y starts at 0 because that's on the x-axis. And it goes up to that parabola, which is given by 3 minus x squared. So those are our bounds. And that's enough to help us set up the volume integral. The volume of the solid region Q is just the triple integral over Q of dV. And you can integrate with almost any order you want, but notice that y goes from a function of x to a function of x, and z goes from a function of x to a function of x. That just means we have to integrate with respect to y and z before we integrate with respect to x. So we'll integrate with respect to x last. Now the other two, the order doesn't really matter because this does not depend on z and these bounds do not depend on y. I'll just integrate with respect to z first and then y and then x. So z goes from 0 to 7 minus x cubed, then y goes from 0 to 3 minus x squared, and x goes from 0 to square root of 3. Okay, now we just evaluate this triple integral. It's pretty easy. There's an implied 1 there. We start on the inside and we work our way out. Leave the bounds on the outside alone. The antiderivative of 1 with respect to z is z. And then we evaluate from z equals 0 to z equals 7 minus x cubed. Then we get 7 minus x cubed when we replace z with that function minus 0, which is of course just the 7 minus x cubed. And then we evaluate this integral. Now remember, you're integrating with respect to y, so you look at this and you say, are there any y's there? There aren't. This is constant with respect to y. Everything on the outside stays exactly the same. The antiderivative of a constant with respect to y is that constant times y. And you're integrating from y equals this function to y equals that function. So you replace y with this and subtract. That gives us the integral from 0 to square root of 3 of 7 minus x cubed times y, where y is 3 minus x squared, minus all of this evaluated at y equals 0, which is 0. So we just get that. And now we're almost done. We just need to evaluate this integral. It's a product. The easiest way to evaluate it is to distribute first. So first times first is 21. Outer times outer is negative 7x squared. Inner times inner is negative 3x cubed. And last times last is a negative times a negative, which is a positive. When you multiply those guys, you add the exponents. That makes that an x to the 5th. And we're integrating with respect to x. Antiderivative of a constant with respect to x is that constant times x. Then here we're going to use the power rule for all three of these. So we bring the constant down, and then we add 1 to the exponent and divide by the new exponent. Then we bring the constant down, add 1 to the exponent and divide by the new exponent. There's no constant this time. Just add 1 to the exponent and divide by the new exponent and evaluate from x equals 0 to x equals square root of 3 and subtract. At x equals square root of 3, we get 21 root 3 minus 7 over 3 times the square root of 3 cubed. Square root of 3 times square root of 3 is 3. And then there's one more square root of 3. So those 3's reduce. Then we have 3 over 4. The square root of 3 multiplying itself 4 times is square root of 3 times square root of 3, which is 3, times another square root of 3 times square root of 3, which is another 3. So it's 3 times 3, which is 9. Similarly, we're going to have 3 pairs of square roots of 3. So it's going to be a 3 times 3 times 3, which is 27, or you can reduce that. That 27 divided by 3 is 9, and 6 divided by 3 is 2. So we end up with 21 square roots of 3 minus 7 square roots of 3, that's 14 square roots of 3. And then you've got minus 27 over 4 plus 9 over 2. I guess we need to multiply by 2 over 2 to get a common denominator. And we end up with 14 square roots of 3 and negative 27 over 4 plus 18 over 4 is negative 9 over 4. And if you're saying to yourself, what's that? That's the volume of this guy. So start by graphing. Use that Calc Plot 3D. Might help you a little bit to figure out kind of what's going on. And then once you've got your graph drawn, figure out the bounds. Z goes from what bottom function to what top function. And then you look at the projection of the region, or of the solid region onto the XY plane. That's this. And then you can describe this as in terms of X and then Y, or Y and then X. Just one variable has to go from a function to a function. The other one goes from a constant to a constant. And make sure the appropriate bounds go with the appropriate variable, the innermost variable, the middle variable, or the outermost variable. And then you just integrate. Pretty simple. Start on the inside and work your way out. That's it.